So we concluded the last lecture by stating these results relating definability in fixed point logic and fixed point logic with counting, FP and FPC, with decidability by uniform polynomial size families of symmetric circuits. In the case of fixed point with counting, circuits with Boolean and threshold gates. So what I want to do now, we stated some consequences of these results. What I want to do now is give you some idea of how these results are proved. So suppose we have a symmetric circuit, Cn, taking as input structures with n elements. Then any permutation in Sn extends to an automorphism of the circuit, and we can assume without loss of generality that the automorphism group is exactly the symmetric group Sn acting in the natural way. That is, that every permutation in Sn gives rise to a non-trivial automorphism of Cn, because if it didn't, that would mean that you had some non-trivial permutation, right? This should be non-trivial pi, of course, which gives a trivial automorphism, which means that for some I, let's say I and pi I, ij and pi ij are actually the same input gate of Cn, right? Where pi I is not equal to I. And if that's the case, then by symmetry, actually, all the gates, are equal, and you can show that the circuit then just computes a constant function. Okay. Secondly, there are no non-trivial automorphisms of Cn that fix all the inputs, because if that's the case, then there's redundancy in Cn that can be eliminated. So we can assume without loss of a generality that the circuit is what we call rigid. That is, that that the automorphism group is exactly Sn. And in fact, one can show, as we do in our paper, that you can in polynomial time convert a circuit into a rigid circuit. So we now assume that this is the automorphism group of the circuit, and we write pi in Sn to denote this automorphism. It's sort of an abuse of notation. It's a permutation of the domain of the structure, which is the input, as well as the automorphism group of Sn. Now, consider a gate in the circuit. The stabilizer group of the gate is simply the subgroup of Sn consisting of those permutations which fix the gate, right? So for which this the gate is not moved by the permutation. And the orbit of the gate G is simply those gates H for which there is a permutation pi in Sn, which takes G to H. The orbit stabilizer theorem, standard fact from permutation group theory, tells us that there is one gate in the orbit of G for every coset of the stabilizer group of G in Sn. In other words, that the size of the orbit is the index of the stabilizer group of stab G in Sn. In other words, it's n factorial divided by the size of the stabilizer group. And we're going to use this in two ways. Essentially, you can see that in order to prove lower bounds on the size of circuits, it suffices to prove lower bounds on the size of orbits. And for that, it is enough to prove upper bounds on the size of the stabilizer. Or look at it another way. If we assume that the circuit is polynomial size, then the orbit of any gate must be bounded by a polynomial, because obviously the orbit of any gate is contained within the circuit. And if this is to be a polynomial in n, bounded above by a polynomial in n, the stabilizer group must be quite large, right? It is n factorial divided by a polynomial in n. So all gates in a symmetric circuit of polynomial size have large stabilizer groups. So an upper bound on the stabilizer group gives us a lower bound on the size of the orbit. And as I said, conversely, knowing that the orbit is at most polynomial tells us that the stabilizer group must be big. Now, what big groups can you get as stabilizer groups of grades? Say you have a subgroup of Sn. We say that a set of elements X in N is a support of the group if for every permutation in Sn which fixes all the elements in X, pointwise fixes all the elements of X, is itself in G, right? So in other words, we say the pointwise stabilizer of capital X is a subgroup of G. Another way of saying that is that G contains all permutations of the complement of X, right? Any permutation which just moves the elements in the complement of X is contained in G. Now, if G has small support, if there is a support of G of size K, that means that the index of that G must contain all permutations which fix the elements of X, and that's a subgroup of size n minus k factorial. So the index of G is at most n factorial divided by n minus k factorial, and therefore it is at most n to the k. So in other words, groups which have constant size supports have polynomial index. In brief, groups with small support are big. And remember, we know that in the circuits we are after, polynomial size circuits, all gates have stabilizer groups which are big. But the converse of this is false. We have big groups which do not have small support. Classic example is the alternating group. Remember, this is the collection of all even permutations of n. Its index in Sn is 2, right? Half of all permutations are even. But it doesn't have any support of size less than n minus 1. So any support for the alternating group is large. What we aim to show is that if you look at the family of circuits, this is the easy direction. If you look at the family of circuits which are obtained from an FPC formula, all right, we know how to get from an FPC formula a family of symmetric circuits. And there, remember what the gates in the circuit look like. For every subformula of our FPC formula and every instantiation of the free variables of that, we have a gate. And we know for FPC there is a constant bound on the number of free variables in any subformula. So the length of this tuple is bounded by some constant k. But now look, the k elements that appear in this tuple A bar form a support for this gate in the circuit Cn. Because any permutation, right, we have one such gate for every possible k tuple, and any permutation of the elements 1 through n which leaves this tuple fixed doesn't change this gate, right? So the support of the gate is simply those elements which appear inside the tuple A bar, and there is a constant size bound on the size of them. Okay, so the families of circuits we get from FPC formulas do have this property that the stabilizer group of every gate has a constant size support. The key for the other direction, right? So we have a translation from FPC to circuits with of polynomial size symmetric circuits, and in fact circuits with small supports. We want to show that an arbitrary family of polynomial size, polynomially uniform family of symmetric circuits with threshold gates can be translated to a formula of FPC. And the key is to show that in these circuits, in polynomial size symmetric circuits, all gates do in fact have small support. So roughly for every polynomial p, there is a k, such that if C is a symmetric circuit on n of size at most Pn, for all sufficiently large n, then every gate has a support of size at most k. right? So k is a constant which depends on the polynomial p and is independent of n. The general form of the support theorem we prove actually gives size of supports in sub-exponential size circuits, and we have been able to push this all the way up to exponential bounds as well, and I'll say a little bit more about that later. So here's essentially how we prove this. I said groups with small support are big, but the converse is false in that the alternating group is big, it has small index, but it has no small support. It turns out, in a sense, this is the only exception because of standard results of permutation group theory. And then we show that this exception doesn't actually arise in the context of circuits, which means that for the groups that actually appear in the as stabilizer groups of gates in the circuit, the converse is, in fact, true. Big groups do have small support. So what is the sense in which this is the only exception? Well, what does it mean to say that a subgroup of Sn has small support? It means that it contains within it the set of all permutations on a large subset of n, right? So if it has if G, which is a subgroup of Sn, has a support X, then all permutations of n without X, which is a large symmetric group, are inside G. So G contains a large symmetric group as a subgroup. That's what it means to have small support. What we can show is that any large subgroup of Sn contains within it at least a large alternating group, if not a large symmetric group. So this is what this statement is. This is a classic result of permutation group theory. For sufficiently large n and for constants k up to n over 4, which is more than we care for, if you have a subgroup of Sn whose index is bounded by n choose k, right? For the special case, assume k is a constant, right? K is some small constant, so this is a polynomial bound. So G is a large group because it has small index. Then you can find a set, think of this as a support, of small size, such that G contains the set of all even permutations of the complement of X, right? So A brackets X is the set of all even permutations which fix all the elements in X. So this is a large alternating group, and it is contained inside G. So any group which has small index in Sn contains a large alternating group. Okay. And what we want to show, what we want to argue is that in fact, for those groups which arise as stabilizer groups in the circuit, they in fact contain a large symmetric group. And how do we do this? Well, this is the restatement of the theorem we just had. We say that if you have a family of symmetric circuits of polynomial size, then all sufficiently large n and gates G have a support. In this sense, there is a set X such that AX, the set of even permutations fixing X, is inside stab G. This just follows immediately from the theorem, right? Because the stabilizer group of G is a subgroup of Sn, and by the fact that the circuit has size at most n to the k, well, we have a polynomial bound on the index of the stabilizer group. So it follows that if you can find an odd permutation that also which fixes X and also fixes G, then the full symmetric group Sx, right, the full symmetric group, or in other words, the pointwise stabilizer of X, is contained in stab G. In other words, X is a support of G, right? Because we already have the alternating group. So if you also have any odd permutation fixing X, then you get pretty much all permutations that fix X immediately are in there, okay? So this is simply the pointwise stabilizer of X, as I said. So now all we have to do is prove that there is some odd permutation of n which fixes X pointwise and also fixes G. And you prove this by induction on the depth of the gate G in the circuit, right? So this is not a fact about groups in general. This is specifically about stabilizer groups of circuits, and it has to do with the fact that these circuits have this inductive DAG-like structure. And this is true at the input gates because each input gate is labeled by some atom, some atomic fact, right? Where R is a relation symbol in our vocabulary and A bar is a tuple of elements in 1 through n. And any gate like this, any permutation that fixes A bar fixes the gate, so the group has small support. So the gate has small support. Now, the induction step. Suppose we have a gate for which this is true for all the inputs to G. We know that G computes a symmetric Boolean function, right? An AND or an or a threshold gate, meaning it is invariant under all permutations of the inputs to the gate. And the circuit is rigid, which means that if you have any permutation that fixes the inputs to G setwise, then it fixes G, right? Because if it fixes the inputs to G setwise, then it must take G to something which has exactly the same set of inputs. But the rigidity tells us that there are no kind of redundant permutations, so it must in fact fix G. So now you consider the set of inputs to G. By induction hypothesis, they all have a supportive size at most k. And suppose, for contradiction, that G is not fixed by any odd permutation that fixes x pointwise. Okay? Which means for any ij, the swap ij moves G, so it must move some element of H, right? Because we know everything that fixes H fixes G. By induction hypothesis, every H has a small support, right? And by this, it follows that the union of those is all in the complement of X. Which means we can then find effectively a large collection of elements with pairwise disjoint support. Okay. This gives us a large number, roughly n over k, when k is small, of distinct permutations. And then we can show that we can independently combine, distinct permutations which move different children H in H. And we can show that we can combine these independently to get effectively an exponential number of different permutations which move G to distinct gates in the circuit, contradicting the assumption that the circuit has polynomial size. Okay, that's a rough sketch. I will let you fill in the details in the exercise class. So, in polynomial size circuits, all gates have small support. This is, roughly speaking, the formulation we get. That, I mean, I stated it for polynomial size bounds. You get constant size support. The more general form is for these kind of sub-exponential bounds. These kinds of sub-exponential bounds, we get upper bound on support size of roughly log of the size of the circuit divided by log n. In particular, when S is a polynomial, this is a constant. So, one way of looking at this is we can get lower bounds on the size of circuits we need for some property by showing lower bounds on the size of support you need. If you show a non-constant lower bound, you get a super polynomial, non-constant lower bound on support size, you get a super polynomial lower bound on the size of the circuit. And we can push that up to exponential, in fact, by strengthening this theorem, and Greg will tell you more about that, that if the size of the circuit is sub-exponential to the little o of n, then you can show that the family of circuits has supports of size little o of n. So in other words, showing a linear lower bound on supports gives you an exponential lower bound on the size of the circuit, which is a bit stronger than you get from that theorem itself. Okay. So now we know that in polynomial size circuits, you can get every gate has small support. Polynomial size symmetric circuits. We write SPG for the support of G. And now we use this to give a translation from symmetric circuits to formulas. Remember, we are assuming we're given a family of polynomial size, polynomially uniform symmetric circuits with threshold gates. And we want to show that the class of properties they decide is definable in FPC. So, what can we say? Now, because the circuit is computable from n by a polynomial time function, that's the uniformity assumption, by the Immermann-Vardy theorem, on this structure, you can define a set of relations which really define the circuit. In other words, you can interpret, using a fixed point formula, the circuit on this particular structure, linear order of size n. We also said that you can compute the support of each gate in polynomial time, and this also therefore can be done in FP because we're dealing with an ordered structure here. Okay, so in some sense all the pre-computation can be done. Now you get an input structure. The input structure is input to Cn, which means basically that you get the elements of A are identified with 1 through n on the inputs to the structure Cn. And then you can show that whether a gate is true on this particular input under this particular assignment of numbers 1 through n to the elements of A depends only on what elements of A are assigned to the support of G. So maybe I should explain this a bit more. We have a circuit Cn, and we're giving the structure A as input. Now we can order the elements of A any way we like and give them as inputs. They're different inputs. We know that the result of the circuit Cn is invariant under this permutation because in particular the circuit is symmetric. So permuting the elements of A gives us an automorphism of the circuit, and the output is the same. Now for intermediate gates, that's not true. For intermediate gates, the result, or the evaluation of that gate might depend upon what order you put the structure A on the input. And what this is saying is, well, it only depends in the sense that it only depends upon what elements of A are assigned to those things which are on the support of G. But the support of G is bounded in size by a constant. So we don't care what other permutations you apply to the elements of A, it won't change how G evaluates. Okay, so this means that we can associate with G the set of those tuples which, when assigned to its support, make the gate G true. And this is a relation of fixed arity in the structure A. Okay, so it's a relation of arity, the size of the support of G. And we can show that this relation associated with each gate can be defined inductively. Right? So we can inductively define the relation which associates with G the collection of tuples. And this induction can be done in fixed point logic. It's fixed point logic if your circuit has only Boolean gates and or and not. If you also have threshold gates, you need counting. And that's how we get our translation to FPC. Okay, that's the sketch of the result. Now I want to say a little bit more. One way of looking at this result is that the bijection game, which was our method for showing inexpressibility in FPC, can be thought of as a method for proving lower bounds for a class of circuits, a natural class of circuits, namely symmetric circuits. The key idea is the following, that if you have a symmetric circuit which takes n element structures on its input, and every gate has a support of size at most k, then if you take a pair of structures A and B, which are, let's say, 2k equivalent, then the circuit accepts A if and only if the circuit accepts B, right? So we've said before that two structures which are equivalent with respect to the logic C2K, or the logic, cannot be distinguished by any formula of fixed point logic which uses at most k variables. Right? We've noted that before. We're saying now something more. They cannot be distinguished by any circuit where the gates have support of size at most k. And this can be proved directly without going through the logic, right? I mean, we have an argument which goes through the logic, because if you have a circuit of support of size at most k, we can translate it through a fixed point formula with a bounded number of variables, and that will give us this result. But I want to think of this directly in terms of circuit by treating this equivalence relation not as an equivalence relation in terms of logic, but just in terms of pebble game. The idea is that if there is a circuit which distinguishes A from B, the circuit itself provides a winning strategy for spoiler in the 2K pebble bijection game. And here's a rough sketch of the idea. If the circuit accepts A and rejects B, then spoiler has a winning strategy in the 2K pebble bijection game. And the number of moves needed is at most k times d, where d is the depth of the circuit. The idea is the following. Spoiler fixes a bijection between the universe of A and the elements 1 through n. And then you show inductively that in the bijection game, spoiler can maintain a pointer to a gate in the circuit such that the current position of the game admits the following invariant. The current bijection, that is the last bijection the bijection alpha includes the support of G. And for any bijection beta between B and N, where beta inverse of alpha takes U to V, the gate G gives a different result when in the circuit when A is mapped to the inputs using alpha, or B is mapped to the inputs using the bijection beta. Okay, in other words, putting A on the inputs with the ordering alpha and putting B on the inputs with the ordering beta will give different results for any bijection beta which satisfies this condition. Okay. So, why is this true? In the base case, if you're at the output gate, then by assumption, we're assuming that the circuit gives us different results for any alpha and beta. It's an invariant circuit, so there's nothing to prove. Inductively, we have k pebbles on the support of G. What does that mean? Well, really, the pebbled position in the structure A is alpha. If the pebbled position is U, then alpha of U includes the support of G. That's what it means. We keep the pebbles on the support of G. And spoiler moves the other k pebbles, right? The support of G is size at most k, onto the support of some child of G. But at each move, duplicator plays a bijection between A and B, right? Because every time spoiler moves a pebble, duplicator gets to choose a new bijection. But duplicator has to maintain that the bijection fixes the current pebbled positions. This guarantees, by our induction hypothesis, that there is some H for which these two are different. Okay, and again, now the H may change over the course of the k moves it takes to place these pebbles, but it takes a little bit of work, but you can show that at the end of it, spoiler has k pebbles on a child of G, satisfying this condition. And so inductively, you move towards the input until you have this condition holding for G an input gate, and that just means that this partial isomorphism, this map from U to V is not a partial isomorphism. Okay. It follows that if you have a class of structures of counting width k, then any family of symmetric serbs, it's accepting C, has size at least n to the k. At least for k, at most n over log n. So we treat this, as I said, we know we have methods for showing certain classes of structures have large counting width, even linear counting width. I said this for satisfiability, Hamiltonicity, three-colorability, XOR SAT. I mentioned these as examples. They all have linear counting width, a linear lower bound. And it follows that you get exponential lower bounds on the size of circuits you need to, size of symmetric circuits you need to decide these properties. Okay, and we'll stop there for now.